I'm here to give you an incomplete guide to C++ object lifetimes. I originally foolishly titled it a complete guide to C++ object lifetimes, and then put the incomplete there again as insurance. And this was a really good thing because it is so complicated and I cannot cover all the details. A lot of it is simply quite buggy in the C++ stack. So this is an incomplete guide to object lifetimes. So now there are two obvious questions. First of all, what are objects? And second of all, what is lifetime? Objects are fundamental to C++. This is a quote from the C++ standard. We're going to see those a lot. Intro.object paragraph 1. The constructs in the C++ program create, destroy, refer to, access, and manipulate objects. So essentially, all you do is manipulate objects in your C++ program. And by objects, I don't mean objects in the object-oriented sense. I mean objects, there are very specific term of art in the C++ standard. And to understand that term, we need to understand three things. The first is storage, the second is value, and the third is type. Let's begin with storage. The fundamental storage unit in the C++ memory model is the byte. And the memory available to a C++ program consists of one or more sequences of contiguous bytes, which have unique addresses. So here's some storage. It's just a whole bunch of bytes, and then I've highlighted one byte. It contains the hexadecimal 0x41. Now, what does that mean? In other words, what's the value of 0x41? Well, it could be an 8-bit integer that happens to be 65. It could be the character uppercase A, as somebody pointed out in the chat. It could be the start of a string that begins with uppercase A. It could be part of a 32-bit integer and just a byte in the middle, and together they make a much bigger number, and so on. So there are various different ways of what an essential byte value can mean, and that is the value. So the sort of Bible for C++ elements of programming says that a datum is a finite sequence of zeros and ones, and the datum together with its interpretation is value. So we've got the bit sequence 0 of 0 and 1s that make up 0x41, and then together with the interpretation, we can get a mathematical value. And a type is essentially this interpretation. A type is a mapping from bytes to some mathematical value. For example, the type unsigned char means we take a 1 byte of memory and interpret it as an 8-bit unsigned integer. The type int means we take 4 bytes, usually, of memory, interpret as a 32-bit 2's complement integer to get the value. Types can be much more complex. For example, string means we need to take 24 bytes and interpret those as pointer, which in turn have additional invariants, a size and capacity. So that is a type. And now an object is something that has a particular type, occupies a particular region of storage at some address, and in that storage, it stores a value. So for example, here we have an object X. It has type int, and it stores the value 42 at some address in our program. We also have an object Y. It's a float, and it stores the value 3.14. And then we can change the value stored at the address associated with X to 11. Now, those are objects. It's important to point out that functions aren't objects, even though they have addresses and live somewhere in memory. For the purposes of the C++ standard, they aren't objects. They just implicitly convert to function pointers, who in turn can be objects. So the function f isn't an object, only the function pointer to f is. Similarly, references aren't objects, they're simply aliases to objects. So X is our object, and then ref is an alias, another name for the object we've declared. But on its own, a reference isn't an object. Okay. Put my time closer. So what is lifetime? Well, objects have properties, and lifetime is one of those properties. But lifetime is a pretty important property, because all other properties of an object only apply while it's in its lifetime. And in particular, before the lifetime starts and after the lifetime ends, there are very significant restrictions on the way you can use the object. So it's pretty important to understand exactly what lifetime is about. So on a very high level, this is how object lifetime behaves. The first step is we need to allocate storage. Every object occupies storage, so we need to allocate some storage. We then initialize the object, which starts the lifetime. And initialize is in quotes there because this is C++, so of course, it isn't quite that easy. After we've done that, we can use the object, we can change its value, we can read its value, we can do whatever. Eventually, we will destroy the object somehow. This will then end the lifetime. And afterwards, hopefully, we deallocate the storage. And this is in a very high level nutshell what's going on with object lifetime. And for the rest of the talk, we will just explore that in more detail in the various cases. Now, it's important to point out the standard is a bit pedantic there. It says that objects can be created. And this does not mean that we start the lifetime. It just means that objects are bags of properties. And when we create them, we've got the mathematical thing we can talk about and assign to properties, but it doesn't actually do anything yet. The lifetime doesn't necessarily start. So you can, for example, say that when you've got a thread local variable, we will, as we'll see, we'll have one object of it per thread. And the declaration on its own doesn't create the object, but doesn't actually do anything yet, because only when we actually start the thread do we get the object. So creation doesn't do anything. It just introduces a name so we can talk about an object. But then the standard uses destroyed, and destroyed actually is an operation. This ends the lifetime. So it is a bit inconsistent there. And I try to avoid the use create as sort of the opposite of destroyed as the operation that starts the lifetime, but I might slip up from time to time. Secondly, lifetime is something the standard invented. It's invented to describe the semantics on the abstract machine. It has absolutely nothing to do with the physical machine you actually execute code. It's just the mathematical specification of C++ uses lifetime to talk about things. And starting the lifetime of an object isn't an operation that maps to the CPU. The CPU doesn't care about lifetime. It's just the terminology of the C++. So a lot of those things are like undefined behavior in terms of the C++ standards, but like the CPU doesn't actually care. And most compilers actually don't care. So it's just some abstract thing to describe the semantics. It's still pretty important. You should still be aware of it. So let's begin. Level 0, variable declaration. I'm going to quote a lot from this sentence, intro.object paragraph 1. Among other things, it says when objects are created, and it says object is created by definition. So here we've got a definition of a variable x. This will create the object, and as we will see, it will also allocate the storage and start the lifetime. We can then use the object, and at the closing brace, we will destroy the object and the lifetime and deallocate the storage. Now, when exactly is the object allocated and the lifetime start? Well, it depends on the storage duration. So the storage duration is another property of an object, and it defines the minimum potential lifetime of the storage containing the object, and it depends on how we created the object. So it's essentially the lifetime of the storage, not of the object itself. And for declarations, we need to know about static, thread, and automatic storage durations. So let's begin. Automatic storage duration is the storage duration of variables in block or parameter scope without any special keywords. And this is the storage that you're all familiar with. It lasts until the block exits. So when we reach our declaration of a variable for automatic storage duration, we allocate storage for it. We can then create a nested scope to allocate more storage of different variables. And when the block exits, we deallocate the storage. And then when the function exits, we deallocate the storage of A. And this is usually not when the actual CPU is going to deallocate the storage, but for the standard, this is when the storage is deallocated. So this is the relevant semantics. Then we've got static storage duration. Static storage is simpler. This is variables at global scope or with special keywords, and they have storage that lasts for the entire duration of the program. So for example, a global variable has static storage, a static variable has static storage, a function local one, or you can even define global variables within a function. All of those have static storage durations, so the storage exists essentially forever. Before we even start executing a program, we have storage for that, and the storage will last until we're done executing the program. Thread storage duration for variables with thread local is similar, but they essentially have a distinct copy per thread, and they're allocated before the thread starts and after the thread ends. So when we've got a thread local global, as soon as the main thread starts, we allocate one copy of storage for it. We can then launch another thread where we allocate another copy for it. When the thread is destroyed, we will destroy the copy. And when the program exits, we destroy the main storage thing. Now, this is the storage duration. And it's really important to point out that the storage duration is not the same as the lifetime. Just because storage is allocated, it doesn't mean the lifetime starts. It's a superset, but not the same. So the lifetime only starts after we've done two things. The first is we've allocated the storage, And the second step is, if we need to do any initialization, we've done the initialization. And only then do we start the lifetime of an object. The good news is, again, for automatic storage duration, this happens at the same time. So as soon as we allocate storage, we initialize the object and start the lifetime. And when we deallocate the storage, we will end the lifetime. There are some terms and conditions that we will cover later in the talk. But in the basic level, unless you do something weird, the lifetime ends. For static and flat storage duration, it's so much more complicated. You have to look at function local static versus global scope. There are constant init variables, dynamically initialized variables. You can use nifty counters. There's the module dependency graph and inline variables. I've given an entire talk about that, another 90 minutes just about lifetime of static variables. You can check that out. I will not go into more detail here. So the standard says that the lifetime starts after initialization, if any is complete. So this is because in general, an object can have its lifetime start without a known value. So to be more precise, when we allocate storage for an object, that object has indeterminate value. And if we then don't have an initializer, for example, it's an int, and we haven't specified an initial value, and there's no constructor to run and so on, then that object retains an indeterminate value until we change it. And if we read an indeterminate value, we have undefined behavior. What this means is this line, int x, it starts the lifetime of an object with an indeterminate value. When we then read the object, this is undefined behavior. It is undefined behavior not because we access an object before the lifetime has started. We have started the lifetime, but simply undefined behavior because we read a value that is indeterminate. But what we can do is we can assign it. And this assignment is fine because we have started the lifetime of the object already. And we don't read an indeterminate value. Instead, we place it. So the second line is now undefined behavior. And then the third line is okay, because by this point, we now have an object whose lifetime has started, and we read a non-indeterminate value. In C++26, this is actually going to change. So instead of being undefined behavior when you read an indeterminate value, it's going to be erroneous. And erroneous is a new term of art, and essentially a weaker form of undefined behavior. So for when you encounter erroneous behavior, the implementation is permitted to issue a diagnostic, and it is permitted to terminate the execution at some unspecified time after that. But it is not permitted to assume that erroneous behavior doesn't happen and then optimize accordingly as it can with undefined behavior. So it's a tamer, more form of undefined behavior that allows more reasoning about it. And that concludes level 0. Are there any questions about the lifetime of variable declarations? Good. So let's move on to level 1, new and delete. Intro.object paragraph 1, an object is created by new expression. And then we've got the delete expression, which destroys an object. So what we can do with new and delete is we can write new int to create the object and start the lifetime. We can use the object, and then we can delete it. Note that there are actually two objects in play here. The first is the int on the heap that we've created using new, and the second is the variable pointer. This is a declaration. It has to do from level 0. And here I'm talking about the lifetime of the object in the heap because we know the lifetime of the pointer itself. And just like with declarations, it is possible to create one with an indeterminate value. So if we write just new int, we start the lifetime with an indeterminate value. So this is undefined behavior because we read an indeterminate value, or erroneous in C++26. So we have to assign it, and then it's fine. And so when we write new and delete, we've got like manual control over when the lifetime starts and when the lifetime ends, which makes it even simpler than variable declarations. So let's talk about something more interesting, temporary objects. Intro.object paragraph 1. An object is created when a temporary object is created, which is a tautology. But what it means is the following. So here we've got a function f. F takes an int by reference. And then we call it with 42. Now, 42 isn't an object. 42 is a value, right? It doesn't have an address. It doesn't live anywhere. To be precise, it's a PR value, not an object. Yet the references are aliases to objects. So what object does the reference alias in the argument? Well, the answer is the compiler creates a temporary object that stores 42 in order to bind the reference to that. This is called temporary materialization conversion, which is a great phrase if you want to win a hangman. And the standard says a PR value of type T can be converted to an X value of type T. This conversion initializes a temporary object of type T from the PR value by evaluating the PR value with the temporary object as its result object and produces an X value denoting the temporary object. This is a lot of words to say a PR value can be stored in a temporary object that contains that value. And this is done whenever we use a PR value where we expect an X value. So like some sort of reference. For example, when we bind a reference to a PR value, like the int to the 42 example, then we need an X value. So we create one using a temporary object. When we do member access, each member has the list pointer, which requires some memory address. So we create a temporary object to have the PR value at that memory address. When we use an arrays really want to be pointers, and for pointers we need some storage. So we again create a temporary object out of the PR value. This is an interesting one. So let's say we have a function that returns a std string by value. That std string has a destructor that needs to run. The destructor is a member function, so it requires a this pointer. So when we call the function without using anything, then you need to initialize the temporary object. Okay. Oh, hang on. There's a question in the QA. Can I? Okay, I'm gonna go the QR question at the end because I can't see them on my second screen. So sorry. Okay, so what's the lifetime of a temporary? Well, when a temporary is created, the lifetime starts. That is easy. And the destruction is a bit more complicated. So essentially, temporary objects are destroyed at the last step in evaluating the full expression that actually contains the point. So we've got a function f that takes a whole bunch of references, and then we call it with 11 and g. Both of those we return in TR values, so we create two temporary objects. And then they're destroyed at the end of the full expression when we reach the semicolon. This means that it is fine to use the references while we're inside of the execution of f, but as soon as we're done and we return back to main, they're destroyed and we're no longer allowed to access them. So you have to be really careful to just store pointers to references somewhere else because there might be temporaries that are destroyed. But there's an exception to this rule. This is called temporary lifetime extension. And it happens in two cases. The first case is when you have a reference that is bound to a temporary, and then the lifetime can be extended to match the lifetime of the reference. So what this means is here we bind 42 to the L value reference int called ref. This creates a temporary object. And then without lifetime extension, the temporary object would be destroyed at the semicolon, which would be quite silly because then ref is just immediately unusable. So instead, the temporary lifetime extension kicks in, and it is only destroyed as soon as ref got out of scope. So we are free to use ref as long as we want to because the temporary is extended, and then it's destroyed when we reach the end of the function. However, you have to be really, really careful about it because it has to be a reference that directly binds to a temporary and not a reference that refers indirectly to the reference. So for example, here we've got the function getStrings. It returns a vector of strings by value. In the first line, we bind that to a reference and have temporary lifetime extension. So here, strings is fine to access because we extended the lifetime of the temporary. In the second case, we are binding a reference to the first element of the vector. This also creates a temporary object in order to do the array subscript. Right? Array subscript is a member function, so we create a temporary object that contains our vectors to string. We then return a reference to the first element of the temporary using from the operator. Right? This is the signature of the operator. We turn a reference to it. And then we bind that reference to another reference. So temporary lifetime extension doesn't kick in because we don't bind the reference to temporary. We only bind the reference to another reference. And that reference in turn binds to something in a temporary, but temporary lifetime extension doesn't see through that. So the second reference in the second case immediately dangles and we're not allowed to use it. So you have to be really, really careful when using temporary lifetime extension. The second thing is when we have temporary lifetime extension in a range-based for loop. So this is actually a much more powerful version of temporary lifetime extension. So if we've got a range-based for loop, we've got the thing after the colon. This is the range expression. And all temporaries created within that are destroyed after the for loop. So this code is fine because the vector string is stored in a temporary that is destroyed when we're done with the for loop. But crucially, this one is also fine. This is because the getStrings temporary is created in the range for loop. So it is extended until we end at the end of the for loop. So essentially, when you're doing a range-based for loop, you don't have to worry about temporary lifetime extension. It will just do the right thing and destroy them once we're done. This is a quite recent change, only 23 or so. And I've been told not all compilers implement it completely, but they intend to stay. So, right. There's a question about move.objects that are erroneous in C++26. No, moved from is never erroneous. You're always allowed to access moved from objects according to the language. You might then just have an invalid state based on a precondition by the class author. So that is temporary lifetime extension. How am I doing this? Okay, great. Okay, I can now use the moment to go over the Q&A. So the question on the Q&A is when the lifetime starts. So we've got int main, int x, cout, we print x. When does the lifetime start? The lifetime starts in the first line. So when you write int x, we start the lifetime, but it has an indeterminate value, and so you're not allowed to read it. But you can assign it already. Okay. Okay, let's move on to placement new. So an object is created by new expression, and there's a special kind of new expression. That's called placement new. And placement new is essentially an explicit constructor call. So if you have some memory, you can placement new an object into that memory by manually invoking the constructor, and then you get a pointer to that. So here we explicitly create an int inside that memory. There is, of course, given this is C++, there's some caveats. Placement new can be overloaded. So you always have to write the colons in front to specify that you want the global version, and then you have to static cast it to avoid pointer, because otherwise there might be like some custom overload that you trigger instead of the built-in placement one. There is a standard library function constructors, which does that for you, but for the placement the other version is sometimes fits better on the side. I recommend that you always use constructors because it does the cast for you and so on. This is the implementation, but I recommend that, but just for slide purposes, I use placement here. Once we've manually created the object, we also need to manually destroy it. And for that, we can explicitly call the destructor by writing dot tilde and then the name of the type. And there's another quirk here. Simply in the grammar, the type that you specify in the destructor has to be a regular identifier. It cannot be a keyword, so you cannot use that to destroy an int, simply because the grammar doesn't allow that. And it cannot have a namespace qualifier. So you cannot call tildes to string to manually destroy a string. This is just a quirk in the grammar, not a quirk in the actual semantics. So you can always work around that by using a type def. In this case, there's a standard library function destroy@, that takes a pointer of type t and then writes tilde t. And here t is an identifier again, so the grammar allows that. So t might be an int, and then we manually destroy an int. But we couldn't write tilde int simply because the grammar doesn't allow that. It has to be a regular identifier, not a keyword. This is just such a bizarre quirk in the language, which is why I always use destroy@. But anyways, placement new. So placement new allows us to create an object in some memory. So how do we get memory without actually creating objects? So we can then call placement new on them. Well, std_malloc as the prime example. Std_malloc allocates storage, does not create objects. So we allocate storage for an int using std_malloc, and then we can call placement new to start the lifetime of the int. We can then use our int as before, and then we end the lifetime by calling destroy@. And again, you would normally just call the destructor manually, but the grammar doesn't allow that, so we call destroy@. And then important, we have to then deallocate the storage because we manually allocated it by calling std_free. A more C++ version uses operator new, but operator new is a global function that allocates storage without creating objects. So the same code, we allocate storage, we start the lifetime, we use the object, we end the lifetime, and then we deallocate the storage by calling operator delete. This is sort of the most common way to allocate memory without creating objects. What we can also do is we have an array of unsigned chars.byte. If it's big enough and suitable aligned, we can put our int in there. So this allocates storage. We can then placement new. Remember, the static has the void pointer to start the lifetime. We can then use it, just end the lifetime by calling destroy it. And then the storage gets deallocated automatically because it follows the same rules as before. So you don't have to worry about that. So this allows us to manually create objects on the stack or in a class variable based on a byte buffer. This is where it gets interesting. What we can also do is we can reuse the memory of an existing object. So here we've got our int x. This follows the same rule. We create an object, allocate storage for it, start the lifetime. We then destroy it. This ends the lifetime, but it doesn't deallocate the storage. So now we've got some storage where we used to have an int at some point, but we've destroyed it. So now there's sort of nothing in there. We can then call placement new to manually start the lifetime of a new int at that same location. Are free to use that new int, and then end the lifetime at the closing brace. There is some subtlety going on here because the closing brace, does it really create the new object we've created, or maybe does it attempt to destroy the old object x again that we've created in the first line but already destroyed? We will get back to that later. But with placement new, we can sort of reuse the memory of an existing object after we've destroyed. And this is perfectly legal code. But you have to be really careful. For example, const means const. When you have a const object and you reuse it, that is undefined behavior. So you're having an int that is const. We then destroy that int. This is fine. You're allowed to run the destructor on a const object. But if you then attempt to placement new something at the same location, this is undefined behavior, because this would mean that we would change the const object, sort of, right? And const means const. Mostly. This exception only applies to const objects with static flat or automatic storage duration. It doesn't apply to const objects on the heap. So if we allocate a constant on the heap using new, we can then end the lifetime and then call placement new on the heap location to create a new object that isn't const with a different value. So const on the heap doesn't matter. So we can change const objects as long as they're on the heap by calling the destructor and calling placement. But for the other storage durations, const means const. The second thing is the destructor still runs. If you end the lifetime preemptively, the compiler doesn't care about that. It will still run the destructor as you've never done that. So you have a std string. We then end the lifetime. And then at the closing brace, the compiler will end the lifetime again. And this is undefined behavior because we're calling the destructor twice. So when you destroy an object, you have to be careful that you put something back in there before the compiler attempts to destroy it again. But this seems obvious. Now, back to this code. We've got our int x. We destroy it. We create a new one. We get the pointer to the new object from the placement new call. We can use that. This is fine, right? We never access an object that is destroyed. But what about this? Can we still refer the name x? After all, we've destroyed x. But then on the other hand, we put a new object in a space. So is this okay? And also a similar thing happens when the compiler attempts to run the destructor, right? It will still refer to the original x when it runs the destructor. And the answer is it depends. So after the lifetime of an object has ended, a new object is created at the same location. Any pointer that pointed to the original object, any reference that referred to the original object, or simply the name of the original object itself will automatically refer to the new object if the original object is transparently replaceable by the new object. So under some conditions, we're just allowed to pretend that we've never changed anything and just use everything as it was before because we've transparently replaced it. What does transparent replacement mean? Well, it's a bit convoluted, so I'm not quoting the standard, but essentially, A is transparently replaceable by B if they use the same storage. So they live at the same address. They have the same type if we ignore CV qualifiers. And then there are three exceptions. Const objects cannot be transparently replaced. Base classes cannot be transparently replaced. And no unique address members cannot be transparently replaced. And then there is some recursion going on when you replace sub-objects or something. So what this means is this code is fine. We destroy our int, and then we put a new int with the same type at the same location. We don't have a const, we don't have no unique address, we don't have base classes. This is a transparent replacement, and it's fine to just refer to x. And also, when the compiler destroys the x object, it is fine because we transparently replaced it. In a way, we haven't really changed anything. We've just put a new object of the same type. So everything just got magically updated to make it okay to access the new object. This is also fine, mostly. So if you have a copy assignment, if you call the destructor and then call placement new, if the original object wasn't const, if the original object isn't a base class, and if the original object isn't a unique address member, this is a transparent replacement, and we're good. But since you as a class author can't guarantee how your class is being used, there is some chance that this is still a bad idea. But in isolation, this can be okay. Similar thing when you do that with a single class member, this can also be done in isolation. There's a question. Will the compiler do an implicit conversion for placement new? Did you replace int with char? So if you mean the argument has the regular implicit conversion rule, but if you have our int and you would transparently replace that by using a char, this is no longer transparent replacement because the int is not the char is not the same type as int, right? So the initializer is the regular implicit conversion, but here you need the same type if you want transparent replacement. You're fine to change it to a different type, but then you're not allowed to access x anymore, right? Because it's not transparent replacement. But you can reuse the storage for any other type that fits. It's just not transparent. So you cannot use the old pointers or names to access the new object. Hope that answers your question. Okay, right. So here's an example of non-transparent replacement. We've got an int that is const on the heap, and then we replace it with a different constant, also on the heap at the same location. We can use the new pointer returned from the placement new, but we're not allowed to access pointer. This is undefined behavior because it is non-transparent replacement. And the idea behind that is a bit obvious now, because the compiler sees, okay, pointer points to a const object. Because it's a const object, it can never change. So I'm just gonna remember what star pointer is and don't bother reloading it ever again because it can obviously never change. And then we change it. And so if you compile that with optimizations on the compilers, star pointer is likely to print 11 because the compiler has reasoned that const object can't change. So this is still going to be 11, even though it's not actually 42. And this is why this line is undefined behavior. It's a non-transparent replacement, so you cannot access pointer. But what you can do is you can launder it. So std launder is a magic identity function. It takes a pointer and it returns a pointer. But the pointer returned magically is allowed to access the new memory. So if you write star launder pointer, this is fine because the launder essentially instructs the compiler, hey, even though you think it might not change, just double check but that actually isn't changed. And so it has to do reload it again, and this will now then also print 42. And this is non-undefined behavior. So if you do a non-transparent replacement, you can launder old pointers to the. This also works with references. So if you've got a reference, here we've got to create a reference to a constant on the heap. We then do a non-transparent replacement, just using the reference as undefined behavior. But what we can do is we can check the address of the reference, launder it, and then dereference it again. And this is then perfectly fine. Okay. I will use an example of memory replacement. So one example of memory replacement in real software is if you in the implementation of std variant. For example, std variant can be implemented by just using a buffer of char that is big enough to contain all the bytes. And then when you put the int member of the variant is active, you put an int in there, and then you put want to put a string in there, then you replace the int with the string in the same buffer. So it's essentially, you can manually implement unions that way. Now, if you think, okay, we've got std launder is great. Std launder is not a get out of UB free card, right? So let's say ints and floats are the same size and alignment. We create a float on the heap, we destroy it, we do a non-transparent replacement of the int. This is fine because we assume they're the same size and alignment. It is then fine to dereference the int pointer because it points to an int, right? And if you've got an int, all good. It is undefined behavior to use the float pointer because we did a non-transparent replacement, so we're not allowed to access the float pointer anymore. So you might say, okay, I'm just going to launder it. Huh? Even if you launder it, you're still not allowed to do it because you've got a pointer to a float, but you don't have a float, you have an int, right? This is still undefined behavior. Launder does not prevent undefined behavior with pointers. It just solves this very specific problem of a non-transparent replacement. If you want to reuse that, this is what launder does. This is all this does, right? It's not a magic thing that prevents undefined behavior. So when do you need to use that launder? Well, if you want to use the storage of const objects on the heap, remember, if they're not on the heap, you can't replace them at all. Base classes or no unique address members. So in other words, never. We will, depending on time, see another use case later on. So this was placement new. Any more questions? Okay. Now it's going to get really weird. Let's talk about implicit object creation. An object is created by an operation that implicitly creates objects, which is another tautology. So the motivation is the following. If you just do malloc, this just allocates storage. But like a lot of C-like programs, then just start using it, right? And according to all rules I've presented so far, the second line is undefined behavior, because at no point did we create a int. At no point did we start the lifetime of it. But this really shouldn't be undefined behavior, because then a whole bunch of C programs are undefined behavior. So what do? Well, in a sort of very unique situation, some operations are specified at implicitly creating the lifetime. And the compiler will do that if doing so would result the program in having defined behavior. So in other words, if it helps you, the compiler creates objects for you. This is the only instance where the compiler doesn't punish you for undefined behavior, but instead does something to make it well-defined. Right? It's a very unique situation where the compiler will actually help you out for once. The caveat here is the object has to be of implicit lifetime type. This is a lot of words to just say an implicit lifetime type is one with constructor and destructor does nothing. As we will see, it's really important. Like the compiler is not going to execute arbitrary side effects for your silence, right? So only if the constructor and destructor does nothing, then it's an implicit lifetime type, and then the compiler will implicitly create one. So constructor and destructor need to do nothing. So which of those operations implicitly create objects? Well, all allocation functions. So std malloc, operator new, std allocator, allocate. And so when you write this code, because malloc can implicitly create the object, and otherwise, if it didn't do that, the second line would be undefined behavior because you don't have an int, right? The compiler will implicitly create an int in there and start this lifetime. So the second line is well defined. How it exactly does that, we'll see soon. Anything that starts the lifetime of an unsigned char is the byte array. So here we've got an unsigned char array, suitable aligned and big enough for an int. We can then just take a pointer to that, assume it's an int, and start using it as if it were an int, because the compiler will see that and implicitly create an int in the buffer to make the code well-formed. Except there's some bug in the standard. For like weird technical reasons, you have to use .launder in order to make this actually well-formed. This is just a bug in the wording. There's a paper that will add the missing language to the wording to make the .launder necessary. So just pretend it isn't there. It really shouldn't be there. It's just a bug that it has to be there. And it didn't want to show actually wrong code, so I've written it, but just pretend it's not there. You're not supposed to need it. But anyways, this will implicitly create an int in the buffer because we need an int in order for it to be well-formed. So memcopy and memmove also do that. So when we've got a char buffer isn't an unsent char or a byte buffer. So this does not implicitly create an object. But when we memcopy int in there, the memcopy can implicitly create an object. So if we then assume there is an int in there, and again, we need this .launder because of the spec bug, pretend it isn't there. This is fine because the memcopy will implicitly create an int in there. But without the memcopy, this would be undefined behavior, because if you just have a char array, this does not implicitly create objects. And then we just assume there's an int when there's never an int. So the memcopy is here the operation that makes it okay. If you don't want the memcopy, use an unsent char buffer. And then it's also okay. You're just not allowed to read it because of the indeterminate values rules again, right? It's all a bit complicated. And then there's a set of implementation-defined operations, for example, mmap or virtual alloc. They will presumably also implicitly create objects. So you can just map a file and start reading integers from that without having to actually create the integers, right? It's what we want to do. Okay, so how does the compiler do that? Well, the answer is uses time travel. So here we've got a buffer that's big enough for an int and a float. And then we roll a dice. And depending on the dice roll, we will either assume there's an int in there, or we will assume that the float is in. And let's say the number is even. So we want to create an int in there. We sort of assume there's an int in there. At this point, the implementation has to travel back in time to create a buffer in the int, right? To make the line well formed, because it isn't the reinterpret cast that actually creates the int. It is the first line that created the int. And you just need a time travel to figure out that it should create an int and not a float. And so as soon as we did that once, now there's an int in there, and this isn't going to change. If we then need a float in there at some later point, well, we're out of luck. The compiler already time traveled back to us once to create the int in there. It's not going to do that again. There's an int in the buffer. There always has been an int in the buffer. There was never any other type than int in the buffer, because the first access is what determines it. And this is also why the constructor and destructor need to do nothing, because time travel isn't actually implementable. So this is just the specification in the standard. Says the abstract machine needs to, like, it doesn't use the term time travel, but essentially it needs to do time travel. And so the actual implementation just does nothing, right? Because the creation of the int does nothing. It's just the birding that makes it well formed that requires time travel. Alternatively, you could say that we have like quantum mechanics going on here. So when you create the char buffer, it contains an int and a float at the same time. And then as soon as you do the first access, it collapses and it's only one or the other. So this is how that works, right? So when you do an access that requires that particular object is at an address, what the compiler is doing, it sees whether it previously executed some operation that implicitly creates objects. And if so, it will travel back in time to that, implicitly create the object of the appropriate time, then travel forward in time and continue on. And from that point on, there is that particular type at the storage, right? And then it will not change. So once we've did that once, there's the int in there, and then any access as a float will be undefined behavior, because we don't have a float, we have an int, right? It's a very weird rule, but it's sort of, you don't have to think about it. It just works out when you just use malloc, and then you start using it as a type. It will just work out for you. And again, implicit creation does not prevent undefined behavior. Just like launder, it's not a UB out of free card. So here we've got our int I. Then we reinterpret cast as a float. We launder it for good measure, and then we access this as a float. This is undefined behavior, because we have an int object. And the compiler will not implicitly create a float object to make your code well formed, right? Because we didn't do one of those operations that implicitly create objects. Also, we have an int. So this is undefined behavior because we don't have a float. We have an int. Now consider we are doing some network programming, and we've got our byte buffer from the network, and we want to read the data struct out of it. This function on its own might be undefined behavior. When we do the access, the compiler might want to travel back in time to an operation that implicitly creates objects to put the data struct in there. But depending on how we obtained that buffer, this might not be possible, right? Only if the buffer came actually from one of those operations that implicitly create objects, is this fine. So depending on how we call it, this might be undefined behavior. So how do we write this function so that it is always okay? Well, we could say, okay, easy, we just use placement new, right? So we placement new our data structure in there, and then we can read it. This is okay. This is not undefined behavior. But the placement new, even though data doesn't have a constructor that does anything, it's not guaranteed to preserve the same bytes, right? So data has an indeterminate value, right? So this is actually a potentially undefined behavior, because we don't touch the like we create a new object with an indeterminate value and we don't get the bytes, right? We sort of logically change the bytes, even though on the actual machine we don't touch them at all, right? So that just does something, does not do what we want. The correct fix is to call start lifetime as. Start lifetime as sort of does explicit implicit object creation. It says, hey, I've got this pointer. Please pretend there's a data object in there, but don't actually change any of the bytes, right? So it's a placement new that doesn't change the object. It just says to compiler, hey, there's a data object in there. There always has been a data object in there. Just pretend there's a data object in there. There's another function that for like arrays, start lifetime is array. Those are 23 functions, I think. So they're probably not actually available, but you can actually implement them yourself. For example, you could do a memmove of pointer to itself. This doesn't actually change the bytes because we just copy them to themselves. But memmove is one of those operations that implicitly create objects. So as soon as we then access the T object at the pointer, the compiler will travel back in time to the memmove in order to create the T there for us. The standard library implementation is actual nowup and not just a memmove, and it also works for like const addresses and so on. But like this is just a fun fact on how you actually can use the semantics to do a memmove that like actually doesn't copy any bytes, but like semantically it implicitly creates object for us. As I said, the entire thing is incredibly convoluted. Now we've implicitly created the objects. What about destruction? Well, there's also implicit destruction of objects. So we can end the lifetime of an object by calling the destructor using destroy it, or by simply releasing or reusing the storage of the object. So for example, here we've got our int object x, then we call placement new in it. This ends the lifetime of the original int object and then starts the lifetime of a new int object. So here we've got implicit object creation. And similarly, when we have an unsigned char buffer, this is an invalid object, right? So we start the lifetime of an unsigned char array. But as soon as we placement new something in that buffer, we end the lifetime of the unsigned char array, and now we no longer have it. Now we just have an int, right? As a consequence, memory leaks aren't actually undefined behavior. So we've got our string, and then we placement new a different string in it. This ends the lifetime of the string without actually calling the destructor. Just because we reuse the storage, do we end the lifetime? So this is memory leak. But this is totally fine. It's just a memory leak. Like it's no undefined behavior. Standard doesn't actually care. And then it will destroy the second string only and not the first string. So those are implicit object creation. 10 more minutes, so we can talk about provenance and understand what exactly launder is doing. Consider this code. We've got two variables, x and y. We set y to 11. Then we do something with the address of x, and then we return y. Every compiler is going to optimize the return y to return 11, because the compiler sees we set y to 11, then we don't change y at all, and then we return, right? So this gets optimized to return 11. But what if this is our implementation of do something? So do something takes the pointer, goes one further, and sets this to 42. And what if it just so happens that that is the address of y? Because they're next to each other on the stack or whatever, right? So do something could actually change y. This would make the optimization invalid because it should return 42 because we've changed it by going to do something. Okay, so maybe this is just undefined behavior, right? Because we don't know whether pointer plus 1 is actually the address of y, so we're not allowed to dereference it. But what if we read this? So we call do something only if the address of x plus 1 is the address of y. And then we call it with the address of x. We do address of x plus 1, which we know is the address of y, set it to 42. The compiler is still going to optimize that to return 11 because the compiler does optimization one function at a time. So it doesn't care what do something does. It sees nothing can change y. So who's actually wrong? Clearly, we're allowed to, we know the address is valid, right? So we're allowed to modify it. But then we also break the optimization So maybe the compiler is wrong. So what's going on here? Well, the answer is this code is undefined behavior. Even though the address of x plus 1 is the same as the address of y, we're not allowed to use it. Just because two pointers are equal doesn't mean they point to the same object. Even though they have the same exact bytes, point to the same address in memory, doesn't mean they're interchangeable. This is because of provenance. So logically, a pointer consists of an address and a provenance. The address is the only thing that is physically observable. This is the thing stored in the CPU register, right? This is the thing that you compare using equals equals. And then the provenance is some weird semantic only thing that identifies the object or location the pointer originally came from. And we're only allowed to dereference a pointer if the address is in the range of allowed addresses for the provenance, and the current provenance of that address is the same as the provenance of the pointer. Otherwise, we have undefined behavior. And crucially, we cannot change pointer provenance using pointer arithmetic. So what this means is in this case, even though the address of x plus 1 is the same as the address of y, they have different provenances. And when we dereference this, the pointer derived from x plus 1, this is undefined behavior because that address has the wrong provenance. It has the provenance of y and not the provenance of x. And we're dereferencing it using a pointer using the provenance of x, right? So we're going out of bounds, so to speak, of the allowed range of the addresses the pointer can dereference. This makes it undefined behavior, even though we are allowed to access the memory at that address, just not via this pointer. And this enables the optimization. With that, we can also understand non-transfer and replacement. So we've got our const object on the heap. This is provenance A. We then destroy it. We then put a new object in there. And because it's non-transfer and replacement, it is a different provenance B. So we're allowed to dereference new pointer because it has provenance B as well. But we're not allowed to dereference the old pointer because it still has provenance A from the A object. But we don't have an A object there, we have a B object in there, right? So this is what's going on there. Only if you do transfer and replacement does the provenance actually change. And now we can also understand std launder. Std launder takes the pointer and updates the provenance to make it valid. And similarly, references have provenances, right? So we can use the reference. You're just using it directly as undefined behavior because of the different provenances. And if we launder it, we give the reference the correct provenance back. But crucially, one of the preconditions of std launder is that there has to be like some valid provenance we can assign to it. So we cannot launder the pointer that is one past the x object, right? Because that pointer can never be dereferenced. So even if we launder it, we will not get the provenance of y. So even if do something were to launder the pointer, because it's just sort of isn't dereferenceable, even if there still was the correct thing, we cannot use it to go out of range of the thing. We can only update it for a pointer that is still in range of the address. If that makes sense. So every object has unique provenances. All objects in an array have the same one, and reusing the memory changes it unless we do transfer and replace. And then we can use std launder to update it. But we cannot use std launder to extend the range of addresses, only to update it after provenance changes. Okay, I have 6 more minutes. Should be enough to do type. So there's really like a lot of material to talk about. So strict aliasing. This code is undefined behavior because you're not allowed to interpret an int object as a float object. But what is actually undefined behavior is the dereference. The reinterpret cast is perfectly fine. Even though you say, well, you can't reinterpret cast between unrelated types, the only thing that is actually undefined behavior is the access. You can only access a type through a pointer or reference that has a type that matches, essentially. What this also means is that the type of a pointer or reference is irrelevant. Only when you actually dereference it or when you do pointer arithmetic does the type matter. But just you can store a pointer in whatever type you want, right? You can decide to only store float pointers in your program, and as long as you reinterpret cast them to the appropriate type before dereferencing, everything is good. It's just a really weird program, right? The type of a pointer doesn't matter. So This isn't a strict aliasing violation because we do placement new, right? We actually replace our int object with a float. So we know d references the float pointer, but we can't do access di because we don't have an int, we have a float. Similarly, when we do start lifetime as, we say, hey, these bytes, assume there's a float in there, and so the compiler does. But it also means because we reuse the storage of the int object for a different object, we no longer have an int, so this is undefined behavior. And you have to be really careful about getting the pointer, right? So we've got an int object, and then we've got a float pointer that points to the int object, and then we put a float in there. We cannot dereference the float pointer because it has the wrong provenance. It has the provenance of the int object because it is derived from the int. It doesn't have the provenance of the new thing. Even if you do the reinterpret cast after. So now there already is a float object at that address, but we still got a pointer that essentially points to the int. Even though the type of the pointer is pointer to float, logically it still points to the int. And even though we have a float in there, we cannot dereference it because it has the wrong provenance, right? We've changed the provenance, so the pointer is derived from the wrong thing. We can either use the pointer returned from place menu, which has the correct provenance, or we can launder it, right? Laundering updated, and now that is okay. Remember, just because you have a pointer of the correct type and it points to an address that stores that type, if you got the pointer the wrong way, you're still not allowed to dereference it because the provenance matters. And this is also the bug with unsigned char buffers that I mentioned earlier. So this code is undefined behavior because the pointer you get is a pointer to an unsigned char buffer. So you're not allowed to dereference it because it has the provenance of the unsigned char buffer. And so I have to use .launder here, but again, this is the bug in the standard. The paper fixes it. There's just some wording missing. So when you want to use .launder in the three cases I've discussed before, or when you're using the memory as storage for a different type, right? Then you need to use .launder to update the pointer. So essentially never, but there are some terms and conditions. And when it originally was introduced, there was like more use cases for it. But now it's mostly useless, so you don't really have to worry about .launder. Okay. There are two exceptions to the strict aliasing rule. You can interpret everything like an signed int, you can interpret as an unsigned int, and everything interpret as char unsigned chars.byte. So the second one is used to access the object representation, the sequence of bytes the object represents in memory. So we've got our int, and then we can do pointer arithmetic to interpret, look at each byte of our int object. Except there's another bug in the standard. You can't really do pointer arithmetic right now because you don't have an array. So the pointer operation is undefined behavior. There's another paper in flight that fixes it. So just pretend this works out. It's, as I said, it's like a really convoluted area of the C++ standard where a lot of what we want to do is well defined. It's actually undefined behavior due to some real technical wording issues and so on. It's a whole mess. Okay. So 1 minute. So really quickly, type panning essentially object of type T1 interpreted as object of type T2. You can do that with start lifetime as we see, but then you cannot use the old name or pointer reference afterwards. You can use start lifetime as to like then start back the different lifetime, but then you cannot use both of them at the same time, and you have to use .launder. So even though we now have an int, you have to launder it because it's not the same object as the original int. It's a different one, right? So you have to launder it. You can also do mem copy, do the type panning, because this doesn't involve object lifetime, we just copy bytes over. So we've got two distinct objects, so we can access both at the same time. They just happen to contain the same bytes. Bitcast is the more modern version of that. And then there's this weird rule where we've got a pointer to the first member, you can reinterpret as a pointer to the object. So here we get the int pointer from the member, access it, and then go back. And that's perfectly fine because there is some exception. This is the wording and so on, not too important. And then via union also doesn't work because when you change the union, you could implicitly create a new object. So this is undefined, the u.f is fine because we've got a float, but u.I is undefined behavior because we changed it, so now it's no longer a float. There's one exception called the common initial sequence. So what this means is here we've got two union members, they both have the int prefix, and then we can access that prefix member using either union member. And this doesn't really involve type panning, it's just that the compiler will magically update the access to go through the active one. So the second line u.b.prefix will sort of has the same effect as u.a.prefix because that's the correct way to access it. And the compiler just silently update it for us. And with that, I am done. Sorry for rushing a bit at the end. I have a lot of material. Personal guidelines. Don't rely on implicit object creation. It's weird. Use placement new after lifetime s, right? Just makes the code way more obvious what's going on. Whenever possible, use the pointer from placement new and start lifetime s directly. Then you never have to worry about launder. And use unions instead of buffers, right? Then you don't have to worry about placement new at all. Just use the union. It's much nicer. The language helps you a lot. Yeah, I don't have time for that, unfortunately. So I can, okay, yeah. So that's that. I work at ThinkCell. We are always hiring for people. So if you want to work with me, we do a whole bunch of cool stuff in C++. And you don't have to know all the details about object creation to work for us. Consider applying. Thank you very much. Hope you enjoyed the talk.